There are two primary types of chemical formulas, empirical and molecular. Empirical formulas represent the simplest whole number ratio of atoms in a compound. Some examples include the chemical formula for water, H2O, PCl5, phosphorus tetrachloride, and CH2O. Again, these are all smallest whole number ratios of atoms. Molecular formulas represent exactly how the chemical compound appears in nature. For example, hydrogen peroxide's formula is H2O2. That's clearly not the smallest whole number ratio possible. That would be HO, but how hydrogen peroxide actually exists is as H2O2. Similarly, CH2O above is an empirical formula for molecules like glucose. You can see that we have the same ratio of atoms, 1 to 2 to 1, in both molecules. But CHO is the smallest whole number ratio, the empirical formula. C6H12O6 is how glucose actually exists. Empirical formulas can be derived from experimental data. For example, we can use a mass spectrometer to determine that maleic acid contains 41.39% carbon, 3.47% hydrogen, and the rest is oxygen. Using this data, we can calculate the empirical formula, the smallest whole number ratio. A general strategy is outlined here, but instead of going through it in detail now, I'm actually just going to apply it on the next slide. When you're watching the video, you may want to get your lecture notes out so that you can review this general strategy in writing as I'm applying it in this problem. Let's start by doing some quick math to determine our percentage of oxygen. If it's 41.39% carbon, 3.47% hydrogen, and the rest oxygen, then we can figure out the percentage of oxygen by subtracting the two given percentages from 100. When we do this, we get 55.14% oxygen. If you look at the previous slide, it says that the next step is to assume 100 grams of sample. In reality, you can assume you have any mass of sample you want. Assuming 100 grams just makes the math easier. The point is to figure, based on the amount of sample you have, what mass of it is actually carbon, hydrogen, or oxygen. If we assume 100 grams, then our 41.39% carbon becomes 41.39 grams of carbon. We assume 100 grams, 3.47% hydrogen becomes 3.47 grams of hydrogen. Again, you can pick whatever value you want, but assuming 100 grams makes the conversions easy. What's really important to remember is that a chemical formula represents not only a ratio of atoms that are in a molecule, but also can be considered as a mole ratio. For example, when we say 1 molecule of water contains 2 atoms of hydrogen, we can equivalently say that 1 mole of water molecules contains 2 moles of hydrogen atoms. So, if we have grams of each element at this point and we convert to moles, we then can derive a mole ratio of elements in this particular compound. Our next step, therefore, is to convert our grams to moles using molar masses. We can see that we end up with 3.446 moles of carbon, 3.440 moles of hydrogen, and 3.446 moles of oxygen. Now we're going to write this out as a chemical formula with these numbers of moles as the subscripts. Now this looks super bizarre. It actually works fine if we're looking at this as a mole ratio, but remember that for a chemical formula, we want to be able to interpret both on the mole and on the molecule or atom level. So we need to actually get this to whole numbers for it to work as an atom ratio. The way we'll do that is to divide each number of moles through by the smallest number, in this case 3.440. When we do the division, even though the numbers aren't exactly the same, it essentially is a 1:1:1 ratio. We typically don't write those subscripts of 1, they're just understood, so essentially we've just determined that the empirical formula for maleic acid, the simplest whole number ratio of atoms, is CHO. Now, this isn't necessarily the molecular formula, and I'll go ahead and ruin the story for you and tell you it's not, but in class we'll figure out how we know if the empirical formula is actually the molecular formula or if they're different.